Bismillahirrahmanirrahim. Assalamualaikum and greeting everyone. Today's lecture we are going to discuss about material characterization techniques, focusing on the X-rays, principle and application. So at the end of the course, definitely students are expected to be able to, number one, to be able to explain the theories and basic concept of related to various instrumental techniques under material characterization course. Number two, we should be able to describe the concept of various instrumental technique. Number three, by doing the related experiment, you should be able to record and interpret the experiment in terms of writing in the areas of materials characterization. And finally, you should be able to analyze the raw data of the finding from experiment that you have conducted according to the characterization technique in terms of accuracy, precision, statistic, graphs, and uncertainty analysis. And the outline of our lecture today is to introduce you what are X-rays and how these X-rays are being generated, followed by the principle of material characterization using X-rays and some related application that use X-rays as the part of the instrumentation part. So what are X-rays? X-rays, if you see the electromagnetic spectrum, we see that the range of the wavelength from the left to the right, we see that on the left is on the left side, which is 10 to the power of 3, you see you will have a longer wavelength in meters, and it goes to the right to be the shorter wavelength. As the wavelength changes, the frequency also does the same, but in different direction, in which that as the wavelength gets longer, the frequency also it works the other way around, in which that it's getting lower. Most importantly is the energy of one photon in electrovolt. If you can see that, you can see that the ranges started from radio waves, microwaves, from left to the right. If you can see the electromagnetic spectrum, EMR. And we have infrared, we have UVVs and soft X-ray, hard X-rays, and finally gamma rays. The energy increases as the wavelength is getting shorter. So these are the things that are related to energy equation. Okay, so these are the phenomenon, and you see that all those electromagnetic spectrum, they are having different sources, from the lower energy to the higher energy, from the left to the right, and the wavelength gets shorter as the increase of the energy. And you know that we have much energy for soft X-ray, hard X-ray, and gamma X-ray. If we separate and differentiating the electromagnetic spectrum, it can be categorized into non-ionizing and ionizing. From the left to the right, you see that those sources that have higher energy will be able to ionize your sample. These are the basic concepts that you can hold, so that you can see some changes of the energy in respect to the wavelength and depending on the sources that we use. Alright, so basically how X-ray are being generated. X-ray tubes is the place, or is the medium and platform for the X-ray generation. So X-ray are being generated in X-ray tube. As you can see in the figure, X-ray tube schematic that you can see in slide number 8. we have a very systematic system in which we have the glass as the front part of it, and we have tungsten filament, we have beryllium window, we have cooling water and target metals, and finally there is the beryllium window is the space or the door for the X-ray to go out from the system after it's being generated. So how these X-ray are being generated in the first place, we see that you can see at the figure we have a tungsten filament. So at the first place, this tungsten filament will be heated, and once it reaches certain temperature, which is after being heated, it can actually produces it can produce electron from the tungsten filament. So this electron will have some kind of energy, and due to the different potential of energy between the tungsten filament with the target, the electron will be accelerated. So the acceleration of the electron from the tungsten filament, that is the acceleration of the electron from the tungsten filament to the target is due to the difference of the voltage or potential between these two parts. And finally, what we can see actually, the electron will hit the metal target. So as the effect of this one, X-ray will be generated from the interaction between the electron and the metal target. We will further discuss about the occurrence or mechanism that takes place at the metal target, but as the effect of this occurrence, the X-ray are being generated, in which it is exiting from the system, which is from the X-ray tube, through beryllium windows. So up to this level, I hope you can understand how X-ray are being generated. Moving on, in slide number 9, we have another schematic of typical X-ray tube operation. This is the same schematic, but it works the other way around. It means that the principle is the same, but the way you see it on the left hand side. Alright, so you know that we have the tungsten filament that we hit at the first place, and the filament actually can emit the electron as the effect of the electron emission. The electron will accelerated to the anode part, producing X-ray. Okay, so the acceleration of the electron is due to the difference of voltage and potential. So X-ray produced when the high speed of electron hit the metal target, and finally it goes out from the system through the beryllium window. This is, if you see in slide number 10, the schematic cross-section of an X-ray tube is normally being used in the lab, and we understand that most of the anodes that are being used are pure metal. For instance, copper, molybdenum, chromium, which are commonly used in X-ray diffractometer application. Alright, so in this system we have a cooling system, so that the heat that was generated due to the excitation of electron or electron production will be covered by the system that is being cooled, so that it's not overheated. Alright, these, if you see the table in slide number 11, we see we have a list of materials that could be used as anode materials. So anode materials is the place that the interaction between the first electron that hit onto the metal, right? So different types of material will produce different sort of energy and reaction. So it depends on certain advantages and sort of limitations, so that it can meet the specific application that it can go. So in generation of X-ray, it involves certain equation. If you see in slide number 12, we see that the X-ray generation can be best described by having the waves and particles in which the energy and wavelength are being considered in the equation. So if you see in the yellow boxes, the first equation, we see that the frequency is equal to the speed of light divided by wavelength. So this is the first equation. Second equation, E, which is the energy in kilo electrovolt, is equivalent to Planck's constant. We have there the number, if you can see, and that is the times by frequency. So this is the second equation. This is a normal and very typical equation of energy. If we merge between equation number 1 and 2 by substituting the equation number 1 into 2, it produces or yield equation number 3. So finally, when we combine these numbers, we will get the energy is equal to 12.398 divided by the wavelength. So this is very common and widely reported to describe the principle of X-ray, in which it involves the principle of energy, wavelength, as well as the frequency. So slide number 13, if you see those equations that we substitute from equation the equation number 1 into the second one, these are due to the phenomenon that you can see that X-ray are being produced whenever matter is irradiated with a beam of high energy charged particle or photon. So in an X-ray tube, normally in a typical X-ray tube, the interaction normally happen between the electrons and the target. So the electron that hit the metal target. Since energy must be conserved, the energy loss from the interaction result in the release of the X-ray photon. Okay. So the energy, which is the wavelength, will be equal to the energy loss, in which in equation 4, energy is equal to 12.398 divided by the wavelength. So this process generates a broad band of continuous radiation, also called Bremsstrahlung or white radiation. In slide number 14, you see there is a figure showing two types of spectrum. We have number 1 is the sharp one, which is the characteristic X-ray, and on the left we have Bremsstrahlung continuum spectrum. So these two types of spectrum are important to indicate the crystallinity of your materials. Bremsstrahlung normally is unwanted spectrum in which that it contribute to the noise of the reading in the spectrum. Bremsstrahlung normally appear as a broad spectrum in which indicating sort of non-crystalline materials. Alright, in the slide number 15, Bremsstrahlung X-ray production, you can see that on the left we have the y-axis, which is the X-ray intensity. On the x-axis we have the X-ray in electrovolt, which is the energy. When we see the German word of Bremsstrahlung means break radiation, because of the collision between any electron. So we see that we have the primary electron from the heated heated filament going to the specimen, which is I mean, like in this case, in the X-ray tube, we have the metal target. So the prime electron will hit the specimen or the metal target, producing some electron that are kicked out from the system. The electron that kick out, or we call knock out from the system, will definitely produce a vacancy. So this vacancy will be filled by the electron from outer shell, and once the electron from the outer shell move or jump into the inner part of the shell, which is the vacancy that created in the first place, there will be some emission of ray, and the emission we call X-ray. So this explains the generation of X-ray within the system. So this is the you see in slide number 16, there is a mechanism takes place to have the production of X-ray. If you can see, incoming electron, which is the high energy electron, will hit to the core level of the electron, and as the effect of the projection of the electron, the high beam, high energy, the electron will be knocked out from the system. As the effect of this one, they produce, I repeat again, it produces a vacancy. So this vacancy will be filled by the electron from the outer shell, so that it will get stable. So as the effect of the jump process, which is jumping process of the electron from the outer to the inner part, you will see that there is a production of X-ray, and the production of X-ray could be at the K shell or L shell, and the emission of the X-ray will be called according to the shell that it produces. Moving on in slide 17, this is like a general information about the use of X-ray in many characterization technique, depending on the aims. If you see in the slide number 18, if you want to do the structural analysis, you could use a various type of characterization. For instance, you could use transmission electron microscope TEM, X-ray diffraction, scanning, tunneling microscope STM, atomic force microscope, or AFM. For composition analysis that is still using X-ray, we can use X-ray photoelectron spectroscopy, XPS, OJ electron spectroscopy, AES, secondary ion mass spec, SIMS, and a few more. For electronic structure, we can still use X-ray electron spectroscopy, SPS, OJ electron spectroscopy, or energy loss spectroscopy. So those listed characterization technique are using X-ray as the principal or part of the instrumentation. We'll be using X-ray within the system. As for now, thank you very much. We will continue in the next lecture. Thank you.